Introducing a pair of gentlemen to take you through a topic that I don't actually understand, so I'm going to learn more than all of you sitting here. This is Patrick and Harris from Census. Patrick is a computer security researcher building specialized IT services for customers worldwide. He is a doctor, not that kind of doctor, the kind of doctor who knows stuff about computer science. He is smarter than I am and will ever be. And he has brought along with him his intern, who is damn lucky to be an intern talking to Black Hat, don't you think?
He does math, actually. He does math, actually. Math, yeah.
I don't know how to do math. So I would encourage you all to pay close attention. Feel free to ask as many questions as you want and track them down. If you don't get a chance to ask questions during the show, remember you can find them wandering around Black Hat. You can ask them questions then. And also, very, very important, fill out your speaker evaluation forms. As a former Black Hat speaker, finding out that nobody filled out your evaluation form is the kind of thing that makes you cry. Please fill out your forms. Thank you.
Thank you very much for the introduction, and thank you everyone for being here. I know there are some very interesting talks going in parallel, so thank you for being here. Okay, so we are going to talk today about how we have exploited the JMalloc allocator, and specifically how we have used all this knowledge we gained from exploring JMalloc and applied it to the case of Firefox, which is basically the most widely used JMalloc application. Okay, so I'm Patroklos Argyroudis, or you can call me Patrick for short. I'm a researcher at Census, and I have worked on the past on topics like kernel heap exploitation, as well as auditing source code and binary code.
My name is Hariton. I'm an undergraduate student at the Electrical Engineering Department at the Aristotle University of Thessaloniki in Greece. I'm currently working as an intern at Census, and I'm mostly interested in compilers, static analysis, heap exploitation, and mathematics.
Okay, so that's a small outline of our talk. Initially, we're going to give an introduction to what JMalloc is, because you probably never heard of it, although you're probably using it without knowing it. Then we're going to go deep into the technical details of the allocator, like the basic structures, its algorithms, and so on. Then we're going to focus on exploitation strategies we have developed for attacking JMalloc, and exploitation primitives we can reuse on attacking JMalloc applications. It is important to note here that JMalloc is a bitmask allocator, so techniques like unlinking and front unlinking are not used by the allocator, so you cannot play tricks with pointers like you used to do in DLmalloc, for example, where gave you a write for primitive. These are not applicable on JMalloc. And then we're going to focus on Firefox and give you an example of how we have manipulated its heap using the techniques we're going to present on JMalloc. We are going to conclude with some of our thoughts on how these attack vectors we have discovered can be mitigated.
So, JMalloc, you're probably using it, but you don't know it. So let's see. JMalloc is a standard userland memory allocator used by libc on FreeBSD and NetBSD. Additionally, JMalloc is the built-in allocator used in Mozilla Firefox, so no matter what the operating system that you're running, Windows, Linux, or OS X, if you're running Firefox, then you're using JMalloc. There's also a standalone version, which you can download and compile and use it on your Linux system. We have been told that Facebook uses JMalloc to handle high load of its web services. And as far as we know, but we're not sure yet, the DEFCON capture the flag is played on top of FreeBSD, so you should guys definitely start JMalloc. So this is a list of the JMalloc variants that we had a look at. The latest FreeBSD and the Mozilla Firefox variant, they are pretty much the same. You can tell that by looking at their source code. The standalone version and the Linux port, those two are also very similar. Our experiments were performed on 32-bit and 64-bit architectures, and mostly on Linux, OS X, and FreeBSD. So why JMalloc was coded in the first place? FreeBSD was in need for a memory allocator that would be SMP capable and that would not freak out when several threads call malloc at the same time. To solve this problem, gmalloc initializes a finite set of arenas, and it actually load balances the malloc requests coming for several threads on this fixed set of arenas. An arena is nothing more than a simple data structure used for bookkeeping information. So, whenever a thread calls malloc, gmalloc assigns either a fixed arena to this thread or a different one every time malloc is called. Depends on the build configuration. There are three algorithms for performing this thread to arena assignment, namely thread ID hashing, an algorithm based on pseudorandom numbers and modular arithmetic, and a very simple round-robin technique. So gmalloc understands that minimal page utilization is not a problem anymore on modern operating systems and computers. You can buy a few megabytes of RAM with a few bucks, so this is not a problem. gmalloc focuses on performance, and to do that, it does its best to follow the principle of locality, which states that memory regions that are allocated together are usually used together as well. And to achieve that, it tries to place memory regions contiguously in memory.
Okay, so to go into a few more technical details on gmalloc, this is a summary of the central concepts used in the allocator. So the basic building block of gmalloc is the chunk. So all the available memory is divided into chunks, and these chunks are always of the same size. This size can be different across the different flavors of gmalloc, but in a specific flavor, this chunk size is always the same. Now, these chunks are used to store both the allocator's metadata, that is the data that are used for managing the allocator, and the user-requested memory allocations, which are called regions in gmalloc. Chunks are furtherly divided into runs, and runs are used to keep track of the free and used regions of specific sizes. As I have mentioned, regions are the item returned when a developer calls malloc, and these are stored on the runs. Now, each run is also associated with a structure called the bin, which stores trees of free regions of the specific runs it's associated with. So, a run may have both used and free items, and if the allocator wants to locate the free regions on a run, it goes through the bin, because the bin has a tree that stores all the free regions on the run. Okay, so that's an image that summarizes what we have talked about up to this point. So you can see here two chunks, chunk 0 and chunk 1. These are of the same size. Each chunk has runs, so run 0 and run 1. And these runs have underlying pages, and on these pages you have regions both free and used. So with blue you can see a used region, and with yellow a free region. Now here you can see this data structure called the bin, which is basically used by the allocator to help it locate the free regions on the run. So there is a tree that contains pointers to the free regions on a specific run. One other important thing to note here is that every single one of those gmalloc data structures has a header, has a metadata structure that is placed in its beginning. So in the beginning of the chunk there is a header, in the beginning of the run there is a header, and in the beginning of the bin there is a header. Regions themselves don't have headers. They're contiguous in memory without metadata in between. Okay, so to go further into some more details, as I said, the chunk is the main data structure, and all available memory is conceptually divided into chunks. Now, the size of the chunk is always the same, but it differs across the different gmalloc flavors. So, for example, on Firefox and on FreeBSD release, you have a chunk size of 1 megabyte, while in the standalone version of gmalloc, we have a chunk size of 4 megabytes. And that's the metadata structure of the chunk, which is, as I told you, is placed in front of the chunk in memory. The important element to note here is the first element of the data structure is the arena, a pointer to an arena, and that's the arena that owns the specific chunk. Okay, some detail that will be useful to us when we go into more detail is that in JMalloc there is this definition called malloc validate, and if that is defined, then there's a global radix tree is constructed which stores references to all chunks of the system. Firefox has this definition compiled by default, defined by default. So the debugging tool we have developed uses this radix tree to locate all the chunks of the system. Now, to go into the arena data structure, arenas are basically the structure used by JMalloc to handle SMP systems and multi-threaded applications. And basically, they manage the memory that is used by the chunks. So an arena can span more than one chunk and page, but that depends actually on the chunk size, which, as I showed you, differs across JMalloc flavors, and the page size, which depends on the operating system. Arenas are used to mitigate low contention problems, because when a thread makes an allocation, that allocation is serviced by a specific arena, and the corresponding deallocation, when it happens also from the same arena. Now, the number of arenas may differ across JMalloc flavors. So, for example, the Firefox version of JMalloc version used on Firefox always has one arena, and that's hard-coded. And FreeBSD has 2 times the number of CPU cores, numbers of arena, and the standalone version has 4 times the number of CPU cores. That's the arena data structure. One important thing to note here is that there is an array of bin structures here that initially has a size of 1. It grows dynamically as regions are created on the JMalloc heap. Okay, so that's a small output from a debugging session. So you can see here that there's an array that stores references to arenas, and you can see here that we print the first arena, which is this one, and also the number of arenas, which in this case is 16, because we're working on the standalone version of JMalloc on a system with 4 CPU cores.
Chunks are divided in runs. Runs are actually simple containers for end-user memory allocations. Each run has a size that is a multiple of the page size, and due to this characteristic, runs are also aligned in memory addresses that are multiple of the page size as well. As we have said, runs contain end-user memory allocations. They actually keep track of the state of each allocation, whether it is used or free. One important characteristic is that a run contains regions of a specific size. So there's no way you can see 32-byte allocation followed by a 64-byte allocation, for example. In order to keep track of the state of each region, a run contains a special bit vector called rex_mask. When a bit is set in this bit mask, it indicates a memory region that is free, and when a bit is unset in this bit mask, it indicates a region that is in use. As an optimization, JMalloc uses a special index in this array called rex_min_elm, which also points to the first region within the run that is free. This is how the run header looks like. Probably the most important field in this structure is the reg_min, right there, as well as the dynamically sized array at the end of the struct, which contains the vector we have been talking about. In JMalloc terminology, regions are the end-user memory allocations returned by malloc. Those allocations are divided in 3 size classes, small or medium depending on the JMalloc brand used, large allocations and huge allocations. Small allocations are usually smaller than the page size. Large allocations have a size much multiple page size and smaller than the chunk size. And huge allocations are equal to or bigger than the chunk size. It's important to remember that small and medium regions are always placed in their own private runs, while large regions, due to their size, require a set of dedicated runs to be serviced. Huge regions occupy a set of chunks, and they are inserted in a global redback tree, which we can use to traverse it using our favorite debugger and find out all the huge regions used in our program.
Okay, so beans are, as I have already mentioned, the data structure that is used to locate the free regions on the runs. So basically, they're used as an organizational structure to keep metadata on the runs of jmalloc. And they organize them by size class. So for example, for allocations of size 2, there's a dedicated bin. For allocations of size 4, there's a dedicated bin, and so on. And also they keep track of the regions on the bin, which of them are free and which of them are used. A bin may be associated with several runs, but a run can only be associated with a specific bin. Now, if a bin is associated with several runs, it has a tree that manages all the different runs that are associated with a specific bin. Now, as I mentioned, each bin has its own particular size class and manages the regions of this size class. And these regions are accessed through the run that is associated with a specific bin. Now, each bin has a pointer to the most recently used run, and this pointer is called current run, and also has a tree of runs with free regions that's called run. So let's say, for example, that a specific bin has a pointer to the most recently used run, and this run has no free regions. So if an allocation is made for the specific size class, then the bin is going to go through the tree of runs with free regions, locate a run that has a free region, return that to the user, and replace the current run with this one, because that was the one most recently used. Okay, so that's the data structure of the bin. Probably the most important thing here is this current run pointer I have mentioned, and this is the tree of runs that have free regions on them. Okay, so that's a small example to make things clearer. So you can see here 3 allocations of size 0, 8, and 16. One important thing to note here is that when an allocation of size 0 is requested from jmalloc, and this is serviced from the smallest possible class size. So in this case, this size class is 2 bytes. So you can see here that for the region size class 2, there has been created an arena that has the current run pointer, which is this one. Now for the size class of 4, there is no current run because there has been no request for size class of 4. Then for size class 8, there is a current run because there has been a request for such a size class. And the same for size class 16, because there is an allocation, there is also a current run created. For region size 32, there is no associated current run because there has been no request for such size, so no run of this size has been created. So I know this all has been very detailed, and probably you were not able to keep up. So hopefully this picture summarizes everything. So here we have the runs, right? And each run has a list of chunks, which are these ones, and each chunk may have several runs. Each run also may have several pages, right? And each page has the regions on them. So a blue region is a huge region, and a yellow one is a free region. Now the bins are associated with the run as with the arena. Yeah, so with the arena. There is a different bin for each different size class, so 2, 4, 8, and so on. Now this bin has a pointer to this current run, and this points to the run that has been most recently used. So that this one. So that hopefully summarizes everything up to this point.
To further illustrate how gmalloc works, we have written down some algorithms using pseudocode. So this is the allocation algorithm. When malloc is first called, gmalloc will call a function called mallocinit that will parse the environment variables and do some bookkeeping. Then the requested size is checked against the chunk size. So if the request size is larger than the chunk size, gmalloc will call a function for allocating a series of chunks. If it is not the case, then gmalloc would call chooseArena, a function that implements one of the 3 available algorithms for picking an arena for this specific thread. And then it checks the input size against the page size. So if the input size is larger than the page size, then gmalloc will call a function that will allocate a series of pages to serve this allocation. Otherwise, the appropriate bin for this specific size class is looked up. Then gmalloc will locate the first run, the lowest run in memory that has at least one free region, and then will traverse its bitmap to locate the first region that is free and return to the user. It's pretty simple, actually. The allocation algorithm is pretty much the same. When a user calls free, the pointer passed to free is checked if it is aligned at an address that is a multiple of the chunk size. If this is the case, then a function is called to deallocate this chunk and actually remove it from the global red block tree used by gmalloc. Otherwise, gmalloc will locate the chunk that contains the given pointer, and we'll use some special bookkeeping information in chunk headers to figure out if this allocation is a large one. If this is the case, then gmalloc will call a function that will deallocate a series of pages and just mark them in the chunk metadata as free. If the allocation is small or medium, the run that contains a specific allocation is looked up, and then the appropriate bit in the big vector is set to 0. So now let's move on to more specific exploitation tactics. Unlike dlmalloc or probably other allocators, gmalloc doesn't use any linked lists. It uses red block trees and radix trees. And of course, as a side effect, there are no unlink on front-link style codes in gmalloc. And this is important because unlinked and front-link have been historically used as the #1 target for exploit developers. Bummer. We need to cover all possible cases of metadata correction. So when you overflow a memory region, you will either overflow adjacent memory, application-specific memory, or probably a run header if the region that you overflow borders a new run. Or you will either overwrite a chunk header if the region you overflow is the last region of a previous chunk. There's also the case of overwriting some special thread local data structures called magazines, but this is not covered in this presentation because Firefox doesn't make use of them. But if you want to have a look at our FRAC articles, you will find there some information on this topic. If an attacker has the ability to leak arbitrary memory from the target process, then he can probably bypass any limitation and do whatever he likes. But this is a strong requirement, and we don't follow it in this presentation. So we focus on techniques that only corrupt very few bytes at the beginning of each data structure. So here's the first technique, the adjacent memory override technique. The main idea is actually pretty simple. It has been used for at least 20 or more probably years. The attacker just prepares the heap so that the target, the overflown region and the victim region border each other. And it triggers the overflow in hope that he overrides a structure, for example, that contains a function pointer or anything useful. Primary target candidates for this kind of attack are the C++ virtual table pointers, if you're targeting a C++ application, or just normal structures that contain function pointers or anything interesting. A very interesting situation we came across was the libpng error handling code. libpng, during initialization, calls send jump a function that saves all registers in a jump buffer. And when it encounters an error condition, it just long jumps to this saved state. So if we somehow manage to override this jump buff, we have a total control of the target process. But okay, you can use your brains and come up with a better idea. It's all about bits and bytes, actually, right?
Okay, so moving on from adjacent region corruption to metadata corruption. So the first thing we investigated with the corruption of the run's metadata. So basically the idea is that you have a region that borders a new run, and you trigger the overflow condition on that last region of the run, and you overflow the metadata that on the new run's beginning. So basically, let's assume that we have an overflow region, a region that we can overflow, that we can trigger an overflow bug on that belongs to run A, and then you have a victim run B that starts immediately after run A. So basically, we studied what can happen when we corrupt the metadata of the second run. So we decided after we have investigated to mess with this rex-min-elm element of the metadata. So basically, by corrupting that, we managed to make the next allocation that is serviced by the B run to return a region that was already used from the previous run A. We haven't encountered a name for this kind of attacks before, so we are using the force-used exploitation primitive name. Okay, so let's take a look at the run header again. So that's the run header, and our goal is to corrupt this rex-min-elm element here. Of course, you may wonder why we haven't corrupted this bin pointer here, where by investigating we found out that by corrupting this bin pointer, this bin pointer is only used during the allocations, and furthermore, it requires a lot of control over the target application's memory in order to be able to manipulate it to gain code execution. So we decided to go for something simpler. So let's see what we can do. So what do we gain if we override this rex-min-elm element? Basically, we can remember that rex-min-elm is an index to this bit mask that help us find the free regions on the run. So by overriding with a specific value, the -2 value, which is this in hex, we are able to make the bit mask point back to the rex-min-elm element itself. So that's the code of jmalloc that is responsible for making allocations. So as you can see here, since we control this rex-min-elm element, we also control I, and since we control I, we also control mask. Then this arithmetic that happens here basically is done by jmalloc to locate the next available free region on the run. But since we control this element here, we are able to make it return a region that is basically 63 slots backwards. But this obviously depends on the size of the region that the specific run is handling. So basically for small or medium bins, we have found out that this offset points to somewhere in the previous run. So basically you prepare the heap and you place some structure that contains, let's say, function pointers or something else interesting on the previous run. You trigger the overflow on this run on its last element, you corrupt the metadata header of the next run, and you make it service the next allocation from the previous run that you control. Okay, so this slide basically says why we haven't corrupted the bin pointer, and the reason that it's only used during the allocations, and even if we decide to go this way, we found out that it requires a great control over the target application's memory content. So that's a lot of work when we have an easier way to attack the application.
So now let's move on to chunk header corruption. The idea is the following. You just have to force two chunks border each other, which is a common case, and then trigger an overflow on the last region of chunk A and override the second chunk's arena pointer and make it point to an existing target arena. So you might be wondering how we're going to find out that target arena. Where exactly is this arena in memory? Well, the first arena of each program is actually initialized at the very beginning of the program. So it usually lies somewhere a few bytes after the BSS section of the target process. So you can even brute force its location. Bring any region in B will now release a region from A. Calling malloc for the same size class will return a region from chunk A that is already allocated and used by the program. This result is very similar to the attack that Patroclus described in the previous slides. So here's the chunk header, and as you can see, the arena pointer is the very first element of this structure. So you can easily reach it and overwrite it. Well, of course, you can make this arena pointer point to a fake arena constructed by you. This is awesome. This can result in a total control of allocations and deallocations in the target memory, but unfortunately it requires a lot of control on the target process. And it's very interesting when you can leak memory from the target process.
Okay, so let's move on to our case study. So when we started looking at Firefox, we decided to work on the OS X platform. So of course we were using GDB to debug Firefox, but we have found out that Apple's GDB is based on the 6.x GDB tree, which has no Python scripting support. And we really needed Python scripting because that allowed us a lot more flexibility in encoding the development, encoding the exploit development tool. So basically we decided to take a newer GDB snapshot and compile it on Mac OS X. A newer GDB snapshot has support for the Mac binary, but this GDB version cannot load fat binaries. Basically we use the LiPo utility provided by Apple to trim down the fat binaries to their 64-bit versions. So if you don't know, a fat binary is basically a binary that has support for both 32-bit and 64-bit macro formats. And by using this LiPo utility, you just strip away all the 32-bit parts of the binary and leave the 64 bits of the binary. Okay, but Firefox.app is a directory that has a lot of binaries in it. So we constructed this, we coded this LiPo debug walk Python script that goes through recursively this whole directory and strips all binaries. Before you do that, you use the fetch symbols utility provided by Mozilla to download all the debugging symbols to allow you to use symbols during debugging, which is very useful. So this basically goes through all this I have just described. So you have Firefox 32.0.1.app. You run fetch symbols on this directory, which fetches debugging symbols from Mozilla. And then you run the LiPo debug walk utility on this directory, which strips all binaries to the 64-bit versions. And then you attach this GGDB, which basically the custom compiled GDB version, the newer snapshot of GDB that's able to load Mako 64-bit binaries and also has Python scripting support and attach it to Firefox. And then you're able to debug it and have Python scripting support. So why do we need Python scripting support? We needed it to develop this utility called unmaskJmalloc. That we basically included in it all functionality we needed during exploit development while we try to exploit JMalloc bugs. So it gives you commands like jchunks, which dumps all chunks, all arenas, runs, bins, all the regions of a given size class, and gives you a preview of their contents, which is very useful as we will see. It also gives you search functionality, so you're able to search all the heap of a JMalloc application for a specific value, which is very helpful in exploit development. And that's the GDB version we were using for all this.
So when exploiting Firefox, we need to somehow create a predictable arrangement in the heap. But unfortunately, uncertainty is the enemy of all attackers. In order to create this predictable arrangement, we use JavaScript and HTML. Of course, you can use any tool you like, for example, BMP files, PNG files, SVG, or anything. It's very important that during heap spraying we trigger the garbage collector so that the memory regions that we free using JavaScript are actually physically freed from the heap. The debugging tools we used during the development were just very simple tools, GDB and Python mostly. So now let's move on to our demo. Okay, we have created a simple shell script that fires up Firefox, sleeps for about 4 seconds, and then fires up GDB to attach to the running instance of Firefox. This is the GDB init file used by GDB when it starts up. The most important line is this one, where we load our debugging tool in GDB. And then we set 2 breakpoints in some general math functions, which we call in our JavaScript code to trigger the breakpoints. So here's the HTML file that we're going to load in Firefox. We have implemented a function called gmalloc spray. It requires 2 input arguments, the number of blocks to allocate in the heap, and the size of each block. We first divide the input size by 2 to take into account the fact that the JavaScript interpreter uses Unicode strings. We then create 2 string constants. The first is called marker, and it contains the deadbeef string. We use this string to locate our blocks in memory easily using our debugger. But you can place anything you like. And the actual content.
Is this better?
Better? Okay. Okay, so then we just, let me use the pointer. Okay. Then we increase the size of, well, I can see, okay, the size of the variable named content. And this is where it gets interesting. We iterate through the number of blocks and actually create this block. Okay. Okay. Okay, and then we create each block by concatenating the marker, the content, and the padding. Okay, now, padding is a random string. We use the padding to bypass some anti-heap spraying protection used by Firefox. When you allocate the same string again and again in JavaScript, Firefox will end up allocating only 1 instance of that string and then use references back to it. So what we do is actually insert a random padding in our string to avoid this mechanism. And last but not least, we insert that block in an array of blocks, and we call substr this way. Okay, this looks strange, but it has to do with the way that JavaScript interpreter represents strings internally. This call to substr will actually force the JavaScript interpreter to flatten the string into one contiguous memory region. We then trigger the first breakpoint by calling this function as seen, and then we deallocate every other block by calling the destructor for the string. But in fact, this call to the delete function doesn't physically remove the region from the heap. So to do that, we need to trigger the garbage collector, and this is what this function does. What we do now is that what we have done now is that we have created a set of holes in the heap, and then we repeat the same process again. But now we spray the heap again, but now the new regions contain the pattern cafe babe. Where is it? Ah, I've skipped it. Okay. Okay. We use the cafe babe pattern. And then we trigger the second breakpoint. If our theory is correct, then we will see dead beefs and cafe babes alternating in the heap. So we fire up Firefox and we're waiting for the GDB to attach to the process. Okay. You have to wait for a while. People familiar with Firefox exploitation know that the libzoo library of Firefox contains several debugging symbols and it takes a little time to load. Okay, so our breakpoints are set. And we're ready to load our XML file. So the first breakpoint has been hit. Let's see now. This is the help message of our debugging tool. We're going to use geruns, the geruns command, to enumerate all runs, all active runs in the heap. It takes a while because our debugging tool has to parse all those bookkeeping information from memory and create a special set of classes. There are several commands in our tool. You can use our tool to search a specific hex string in memory, list all chunks. You can do anything you like when it comes to gmalloc exploitation. It takes a while. Okay. So our exploit targets the 512 run. As we can see, this is the address of this run. And we're now going to list all regions that have this specific size. Oops. See regions. Okay. So as you can see, the first heap spraying resulted in several of those allocations containing our marker, the first marker called deadbeef.
Okay, so the columns here.
Yeah.
So the first column is the index of the region. The second column is whether it is used or not. The third region is the actual address of the region. And the final column is a 4-byte preview of the contents of the region.
Okay, so we're ready to continue. 1 minute. Okay. Okay, we have now hit the second breakpoint, but we have to parse the memory structures again because the heap layout has changed a bit and our debugging tool caches the previous results. So we need to flash them from memory and reparse the whole structure.
Yeah, we do this caching because it allows the tool to run faster when you're in between, when you're during the exploit development and you are sure that the memory layout has not changed. So instead of every time at each command reparsing everything, it just caches it the first time you run a command and then it goes through these structures it has cached to make it run faster. But since now we know that the memory layout has changed, we run jparse to reparse the metadata structure of jmalloc.
And then we list the runs again. Okay, so this is the 512 run. And this is the previous value that we saw earlier. As you can see, the 512 run hasn't changed. It's the same. So let's list again all regions that have this specific size. Yeah, and this is what we call beauty. You can see the Cafe Babe and Deadbeef patterns alternating. Did you like it? Okay.
Okay, so these slides basically explain what Harris has been talking about. Okay, so we have another small demo to go through. In order to work with a real exploit, we decided to use this integer overflow in limpng, which is basically when limpng tries to decompress a compressed PNG file. And that leads, there is a bug in there that I will explain in a second, that leads to a heap allocation that is actually smaller than the one expected, and that subsequently has a mem copy that does a heap buffer overflow. Now the vulnerable Firefox version is 10.0.1, which contains the vulnerable limpng version 1.2.46. Okay, so that's some code from limpng that has the bug. Okay, so here is the vulnerable malloc call. We control prefix size and expanded size through the PNG file, and we can make this overflow. And by overflowing it, we control the return size we control the size that is actually allocated by malloc. And therefore, we control not the exact address that this region has, but we control which run this region is allocated on, based on its size. And then we have this mem copy call here that basically overflows into this text variable allocated here. And it copies data from the PNG file, which we control, up to prefix size bytes, which we also control through the PNG file. Okay, so how do we exploit this? We decided, you can also use metadata corruption, but you will see it's much easier to do adjacent region corruption in this case. So basically the integer overflow, as I have already showed you, allows us to control the size of the allocation. So we select an appropriate size class to attack. For this example, we selected the 1024 size class. So the first step is to spray the runs of this size class with an appropriate data structure that has interesting things in it, like function pointers. You can select objects from Firefox to do that. For this simple example, we just use the deadbeef string to simplify things. And then we freeze some of these allocations. We trigger the garbage collector to physically free them on the jmalloc heap. And this creates slots, gaps of free slots on the run. And then we load the crafted PNG file, which fills those gaps and triggers the overflow, which overflows into the deadbeef structure, which is just a string for this example, but in reality, it could be a structure with function pointers. So since we developed this exploit on Linux, we will just show you a video of it. Okay, so basically we're targeting Firefox 10.0.1 on 32-bit Linux. We again have the same script that loads Firefox and attaches GDB. That's the GDB init file, loads unmasked jmalloc and sets some breakpoints related to the specific bug. So that happens here. That is Firefox, and GDB attaches to it. It takes a while to load the libzul symbols again. Yes, sorry about that.
Yeah, it's kind of faster on Linux actually.
Yeah, it won't take as long as in the OS X case. Okay, so now our breakpoints have been set. You can see that this is Firefox 10.0.1, the vulnerable version. Now we load the HTML file that does the heap spraying and creates the gaps, and then loads the PNG file that triggers the bug. So all this happened with this HTML file that we're going to load now. So that's after the actual bug is triggered with the PNG file. The first breakpoint that will be hit now, okay, this takes a while now because this PNG file is a compressed one, and Firefox decompresses it, and this is where the bug is triggered. So that delay here is that decompression done by Firefox. Okay, so now the bug has been triggered. So that's the vulnerable malloc call. You can see that we control prefix size, we control expanded size, which we have set to this value to do the overflow. Now this prefix size plus expanded size plus 1 is the actual allocation done by malloc, and this returns, sorry, let me pause here. Okay, so that's the actual allocation done by the malloc call here, and after the integer overflow, that is 2EC in hex, which is 748 in decimal, and this 748 allocation goes into the 1024 run. Now, we move a step here on the allocator, and we can see that malloc has returned this memory area here. Actually, okay, so now the value of EAX is printed. So this memory here is the region that malloc returned, and that's on the 1024 run. And remember that at this stage, the breakpoint has been hit after the initial spray, the creation of gaps, of holes on the heap, and the loading of the PNG file. So we will now list all the regions of 1024 of the 1024 run. Again, that takes a while because it parses the structures from memory. Okay, so here we have all the structures of the 1024 run. Now, the important thing to note here will be highlighted by the video, but I will explain it as well. Sorry. Okay, so what we see here is that after the overflow, malloc has returned this region here, which is this region, right? But what we can see here is that the next region that is adjacent to this one has this value that we have sprayed the heap with. So when we trigger the overflow on this, it overflows here. And if you put a data structure here that contains function pointers, basically you've gained control of the execution of Firefox. I don't think the video has anything else here. Yeah, so basically that's it.
So as we can see, Firefox exploits heavily rely on the fact that we can arrange the heap in a spatial way. So what can we do to avoid such problem? The latest gmalloc implementation uses some red zones. Red zones are just simple memory regions that fall within end-user memory regions that are filled with a standard pattern. And whenever an end-user region is freed, gmalloc will just check that this pattern is the same. If it's not, then it's probably an overflow condition. Okay, this is cool, but it's disabled by default because it results in a huge overhead. So there's another technique involving randomizing the allocations. So whenever you call free, the pointer you pass to free is actually inserted in a linked list. And instead of physically freeing the passed pointer, free will just pick up a random chunk from that list, region from that list, and free it. This is cool as well, but unfortunately it breaks the principle of locality because the next time you call malloc, then gmalloc will probably return a memory region that is on some different page, thus breaking the principle of locality, and of course breaking the efficiency of the allocator. Here's the code that implements the red zones in gmalloc. As you can see, during the allocation of a small or medium region, this pattern is repeated right after the allocation and before it. And during the allocation, it just checks that the bytes are the same. If not, then this error flag is set to true, and the program terminates. Yeah, of course you can bypass that by overwriting the same byte, right? It's easily bypassable even if it is compiled by default.
Okay, so in conclusion, what we're seeing is JMalloc being increasingly used because it's a high-performance allocator, because it has specifically been developed with SMP systems and multi-thread applications in mind. And although we have seen a lot of software packages like FreeBSD, NetBSD, the Firefox browser, and even Facebook using it, there hasn't been any security assessment of the allocator so far. So we've done the first step towards that goal. Of course, there's a lot of work to be done as well, so feel free to build on top of our work. Again, the most important thing to probably take out from this presentation is that we're seeing a move from linked list-based allocators to bitmask allocators because their performance is much better. So the old exploitation primitives of front linking and end linking would grant you a write for primitive are no longer applicable. You cannot use this kind of technique. So new exploitation approaches need to be developed. So what we did is we tried to find one of those, and we came up with this thing we call the force used primitive, which, as we have explained, returns an item that the allocator is already using, is considered to be used. And we have also shown how you can use all this JMalloc knowledge to attack probably the most widely used application that uses JMalloc, namely the Firefox browser. And we have also developed this unmasked JMalloc utility that we hope, if you're doing any kind of JMalloc exploit development, to use, and feel free to enhance it and submit patches to us. And we're going to be very open with its development. So please contribute if you do any kind of JMalloc exploit development. Okay, we'd like to thank all these people here because they talk to us on various heap exploitation subjects and also on JMalloc exploitation. So the feedback has been very helpful. Okay, these are the references. As I told you, we are going to continue developing unmasked JMalloc, and this will happen on GitHub, so feel free to do any pull requests for us there for code you have written. And basically, that's it. That concludes our presentation. If you have any questions, we will be happy to answer them.
What do you think will be the most challenging part of future? Reliability, is it future improvements being made, like what in April, or what is the biggest challenge?
Okay, I don't think there's going to be much of a challenge in trying to develop bypass for the mitigations, because what we have noticed is that mitigations on this kind of allocators are very difficult to implement, because all kind of mitigations you may come up with basically have a huge impact on performance. And since this is the main goal of this kind of allocators, they don't really enable them by default or actually spend much time implementing them. So I would say that that's not really much of a challenge. The real challenge would be to follow up on the changes of JMalloc, see if these attacks are applicable, maybe come up with new ones, right? So we have, if you go through the presentations again, you may see that we have some pointers on things we haven't really looked at, but we started looking. So that will give you some pointers on going to continue our work. I mean, if you have any more specific things to ask, we can talk offline. Any other questions? Okay, thanks.
Thank you very much.
Thanks for being here.